The mirroring unfortunately doesn't work, so this is why I'll hold the mic and be looking this way for the talk. The talk today I'll give in two parts, mostly, with a quick background explanation of how this fits into a larger picture. The first talk will be more of a system-y talk on what MeshCI is, why I'm building that, and how it works on a high level. And then the second part is something which is maybe more Scala specific for Scala Days, is how I solve a recurring problem, which is defining a direct style API, but actually manipulating first-class objects. So just a tiny bit about me. I've used Scala a long time. My introduction, I haven't used it since, but my first time I saw it was when large capital int was still written lowercase int. I am an independent developer, and I am building a software delivery system which is called actually MeshCI, so that what I'm presenting is going to be a part of it. Quick pitch of this is releasing software is a pain, and I'm trying to solve this. The thing is that what often happens in organizations is either you have teams which work in complete isolation. Integration is very rare between teams. It leads to the traditional development where you have freezes every so many months. Nothing gets done, time is wasted. Or the other situation, what you often see is someone says, let's use integration, continuous integration, implements it naively, and basically everyone is slowed down. So either way, this creates a lot of frustration. And the problem really, why does this exist? First of all, large organizations have teams to fix this. Smaller organizations, the problem just exists because it's no one's job. It costs money. It's not mission critical. And what I'm building is in the theme of what we saw of Scala is convenient and safe platform which can basically address this problem. The core idea here is that instead of having an all or nothing approach, you take a more fine-grained approach in tracking dependencies, only testing what is necessary. I promise I'm getting this is the intro of how this workflow manager fits in. So the platform that I'm building is kind of built on three major pillars. The first one is, of course, the dependency tracking. This allows projects to be, it doesn't impose a structure, so it can be monorepos, one project per repo, anything in between, really. And then the other pillar is going to be gathering tests. So this allows you, an organization, to get basically an overview of all tests across all projects, which helps identify when the time is right to do a release, and also identify flaky tests. And then, of course, how is all this glued together? Well, you need an engine which can actually automate a bunch of tasks. And this is where MeshCI Workflows fits in. Initially, it was developed as the automation which runs tests for my platform. However, it turns out you can also use this to write user-definable tasks, for example, for custom CIs or release processes. You can use each of these platforms on your own, by the way, or that's the plan, or as a whole. Just to mention it, most of this is written in Scala, and today I'll be focusing on these workflows. So let's take a step back. What actually is a workflow engine? If you search this on Google, you'll find a Wikipedia entry which basically means nothing. If in context, what I'm talking about here today is basically going to be a system which manages, orchestrates a bunch of software development related tasks that happen on certain events. This is often also a specific case of this is continuous integration, continuous delivery, continuous deployment, you name it. The important insight on a workflow is that workflow consists of tasks, and tasks depend on each other. So together they will form a directed acyclic graph of dependencies. Let's look at some more concrete examples. So I'm sure many of you have come across some of these. There's, for workflow engines, you have things like GitHub Actions, Jenkins, if you know, many, many more. You can even think of a deployment tool, such as Spinnaker, as a specific kind of workflow. Many examples you'll come across in software development are tasks or automations to run your tests when a user creates a pull request, or publish software when someone pushes a tag, build your nightlies, etc. You can even do this on the deployment front, where you say, I somewhere have a configuration template checked in. This configuration template works in conjunction with some Docker image, and if any of these are updated, I want to update my deployment config, maybe ask a human to review, and then deploy it. So these are some examples. If you look at this graphically, you can naturally see the DAG structure, right? So this example here, the first one was saying if you clone a repository on a push, what are you going to do? You're first going to clone it, then you're going to build it, then you might push your resulting binaries. And importantly is also that this is really a graph structure. This is not necessarily a linear sequence of steps. So in this situation, on a pull request, you might want to say, first I clone it, then at the same time, I'm going to spin off a job which checks my style. I'm going to build it, and then I'm going to massively parallelize all my unit tests, because unit tests are great to be parallelized as much as I can. So you really see this graph structure that comes out, and the order of sequences is not necessarily important, how they are run. It's just that the dependencies, the tasks before them, have been run. A final example here really is the, back to the deployment example, is I have this configuration template that's checked in. The image, if either of these change, I want to materialize new configuration, display this to a human, and then deploy it. The deployment itself could then again be a trigger of a workflow, so you really see this kind of graph structure is everywhere. So these tasks might not seem like anything new or exotic. You're probably very familiar with them. So the question then is, why did I build a new one? Well, it's an internal tool, but I wanted something where I can define my tasks in direct style Scala. I don't want something monadic or DSL heavy. And definitely, I don't want to have to use a UI to specify my tasks. And most definitely, like unfortunately, many workflow engines require you to write YAML. And if you want scripting in YAML, it's, yeah, you really don't want that. I also want this thing to be runnable on my laptop, so I can test it. Because imagine if we applied this to other software principles. Like, you can only test in production. Like, this is a no-go, so you definitely want to be able to run it locally. And unfortunately, also many tools just either are proprietary, don't make it available to you, or are more difficult to set up than it is worth and what you get out of them. Then also, I'm not in the hosting business, so I want this tool to be either runnable on a single machine, such as piggybacking on GitHub Actions, or if you do have a cluster that's just sitting there, you could use all the machines you have and essentially, yeah, just parallelize as much as you can on them, as many machines as you can. So I'll show you a quick demo. This is going to be very minimal, but it'll show you, hopefully show you the gist of what this system can do. Is this large? Oh, it's maybe too large, huh? Okay. So as I mentioned in the talk description, a task is defined just in direct style Scala. So the top parts here you can ignore. The really important thing is that every task in my workflow diagram, in my workflow DAG, is defined essentially as a def. So these, I wrote them as vals. These can also be defs. And the only thing that kind of distinguishes them from, let's say, normal direct Scala prose is this task block here. I'll explain what this does. I hope you can kind of guess, at least if you can, and I'm happy that the DSL is nice. The first task here is, so essentially every task has a body. It's going to do something and it's going to return something. So in this case, I'm just returning a string literal. Of course, in reality, you can use your favorite HTTP client. You can shell out to Git, whatever you want. This example, I'm taking the configuration and software deployment example. So the first task is basically going to fetch this image where I say, this $img is going to have to be replaced later on. Then I have something which would fetch the actual image. And then we can get into a more interesting task, which is basically going to say, I'm going to need the result of a previous task and then do something with it. So in this case, again, it's simple. I'm just going to wait in the loop just to also slow things down so we can see this a bit better. I'm also going to interact with the environment. So I'm going to log a message. Why am I not using print line here? So usually you could just print line. Now you need to think this workflow engine can be run on multiple machines. So every task can be run on a different machine. So basically, if I were to print, it would just be printed to the standard out of whatever JVM is running this task. Logging is going to be something that's somehow implemented by the environment. I'll show you that in a moment. And which allows us to get all logs and see them in a nice UI. So this is just one case of interaction with the environment. And then, well, the task does some actual interesting work. It returns the result. And then finally, I just have a couple more tasks which are there to show you what happens if there's an error, if one of these tasks fails, and what happens if another task that depends on a task that has failed also fails. The way you run this locally is I have the runner file here. I just give it run. I just call it, and I give it the file name that I want to run. And then I'm going to refresh this page. It has a UI where you can see what happens exactly. So you see there's a graphical representation of the structure of tasks that is materialized here. It's being evaluated live. So well, I was a bit too late. I'll just restart this. So you can inspect every task. You can see live what's coming out. So here we have this loop that you saw earlier. And you can basically, if something were to go wrong, you could immediately see, the task, what's happening inside here, and this would hopefully help you narrow down what is happening very quickly. So that's kind of the very basic demo. I ran this locally, but essentially, what did I do? I spawned the running VM, I spawned the UI, but these are all separate components and can be distributed in different ways. The important things here is we've gone from a direct style Scala file into some runnable task graph, which we have serialized, same machine, but could have shipped to another one, ran, and we've inspected the graph to get analysis of it, reporting, and many other things. So the first 2 points is where we can really leverage Scala, the language, and the JVM as well. The second 2 parts are more of a systems problem, which is very interesting in its own, but I'm not going to focus here on this talk. But in case you just are curious, so the tech stack to implement this is, I've used Scala, this is Scala JS UI with Scala tags. The web server is based on Cask. Scala PB, which is the protobuf implementation for Scala, and upickle are used for serializing the objects, and mill is used to tie it all together. Fun thing is actually Scala PB. I'm using the Scala PB implementation in the browser as well, so it's kind of fun that works without a problem in Java in Scala JS. So Scala PB in Scala JS. Okay, so for this talk, like I said, I wanted to concentrate on the question of how I can get from this direct style into this higher level language, which can then be used to be run on my whole system. And to do that, the first thing we should ask ourselves is, why is direct style actually not sufficient to define workflows? Because if you look at it, you could basically execute this as is almost. You just remove the task blocks, replace them with functions, and why should I care? Well, the thing is, for workflows, you need to be able to manage these tasks as isolated units. So I also want to get metadata about them so that I can enable all these debugging features that I mentioned, and reporting and everything. You saw that makes a workflow engine a workflow and not just a direct executor. So put a different way, on the one side we have this nice human-readable direct style language for our workflow. And on the other side, we have something that's not really human-friendly, but that's what actually is used by the machines. So in this case, I've defined this as like pseudo proto buffer. Essentially, what I'm defining here is I'm shipping a DAG, a graph, which is serialized as a list of nodes and a list of edges. So the question really becomes is how do I get from the direct style to the machine representation? And one way to do it, as you do with many things in computer science, is you introduce indirection and you reformulate the problem. So I'm going to say, assume I have an intermediate structure that can be serialized. How could this structure be represented in direct style? And then I could go back. And the answer there really is, well, let's just use plain Scala, plain case classes. Serialization is already something that's quite well understood, many options. And direct style, I'll talk about how we do this. So the first thing you'll see here is, or actually let's take a step back and let's look at mappings. There's some correspondences between these three different representations. So the first one is you'll note every task block that I've declared becomes an instance of the task case class and will also become a node in the serialized version. Then metadata, such as task names and syntax of the actual block. The source code is something I also want to capture. These will become fields in my case class and also be serialized again. And now the more interesting thing is what happens with the payload, with what I want to run in the task. On the right-hand side, you'll see this looks like a plain list of statements, just a block. Now, in my object definition, this is actually has become a lambda which takes a parameter. And in my serialized version, it's just a bunch of bytes. I'm not going to get too much into that. But the real question is, why is this parameter there? Where did it come from? And yeah, how do we get there? And to answer that is we need to look at another thing, another feature of the direct style and first class object mapping. So the thing is, what happens if in the direct style I want to use the result of a different task? Well, in my syntax here, I'm just calling the apply empty paren method. And what I want this to do is, well, first of all, I want it to declare a dependency on this task. So that's fine. This dependency then will also get serialized as an edge. However, remember at runtime, these things can be run on different machines as well. So there's no way I can actually get, like in my Scala code, I can't say, hey, you task, give me what you contain, because the task doesn't contain anything. It's just a definition. So I need to pass in something from which I can interact with the environment, so from which I can get my results in this case. So this is why I need the representation of the task body to become a function that takes in an environment parameter. And this will later on be rewritten to something of environment.get, call res with the task that I'm interested in. The same thing goes for logging. This might be more immediate. If I want to log, as I mentioned before, this is an interaction with the environment. This will need to be calling a method in my environment, in my first class object representation. So that's why we need to transform this direct style parameterless body into something that does take a parameter. Okay, so now we've seen the mappings here. Let's look at how we can go from one step to another. From the object representation to the serialized one, that's quite, like I said, quite well understood. The only brittle thing is how do you serialize the lambdas? If you're curious, you can look, well, I mean, JVM has a feature to do that for you. It's a little bit brittle. You can look into what Spark does if you're curious. Or another interesting avenue might be to use something like spores, what Jonas and Philip talked about. But what we are interested here in the talk is how do you really get from this transformation, this is the direct style, into the first class object one. So to do that, we're going to use two features of Scala, context functions and metaprogramming. And these two features, they kind of map to the types of structure, to the types of mappings I've just shown you. On the one hand, we have this thing of the syntax sugar that's provided by Scala syntax sugar, which is saying, well, this env, where does it come from? And then the other one is things that we can't really do on just the regular Scala level where we need to actually go into our the program tree, which represents what is in the body of a task, and manipulate that. And for that, we will use metaprogramming. In the past, I've done actually a talk where I dig more into these details in a different context. So if you are curious, you can check that out. But now I'll focus on really these two concepts and how we can bring them together. So I'll do an introduction on context functions. So what are context functions? In a way, or one of their use cases is essentially to hide implicit parameters. So I think this can best be shown with an example, which is going to be similar to the task definition. Let's assume I have this withenv method, takes as parameter a function that does something with an environment. So an example would be, let's say I want to log. Let's say assume there again is this log method somewhere that needs an environment, and I want to just call that. Well, closure, no surprises. You would work with the env parameter. You could, if this log expects an implicit parameter, you just pass it with a using env. Now, if this situation happens a lot, so if you have a lot of these use cases where you have logs all over the place, the fact to having to specify an env parameter really is more boilerplate than usefulness. If the context you're in makes sense, right? I'm not saying you should use this now in everywhere. So a context function in Scala really allows us essentially to replace the function definition. Instead of being an arrow, it's a question mark arrow. And then we can, in our, when we call this, we can essentially just not declare the parameter, and it will be inserted just as I've shown you above. The other thing is, the other concept are macros. So this is a very first introduction to a macro. Essentially what they do is they allow you to, instead of working with values that are passed to a macro can actually inspect the structure of a Scala program that is passed to the macro. So again, I think this can be shown quite simply with an example. In this case, I have a function called show1, which just takes integer, gives you the string representation, and show2, which does something similar, but does more. Instead of giving you just the string representation of the value, it gives you the string representation of the actual expression I've passed it in. So you can see this down here, where if I will have a value x, which is defined to 1, I add 1 to 1, of course I get 2. This is no surprises here. However, in the macro version, I actually see what I have passed in. So instead of getting 2, the value, I get the expression. And I can also manipulate it. I'm not showing this. I'm just really showing what you do. And the way this works on a high level is a macro is implemented in 2 parts in Scala. You have a definition, a declaration, which is you can identify with an inline keyword followed by a body with this $. And then there's the definition or the implementation of the macro, which has a corresponding signature, except you'll note that every parameter of type t becomes this expression of type t, and the macro also returns, again, an expression of what the original function returns. And essentially, this allows us to do manipulations with the expression we receive and splice some version of it back into the caller. So that means instead of the caller getting the value of my macro, it's getting an expression that is going to be the body of whatever this is assigned to. Okay, so we have these 2 concepts. Now, how can we use them to essentially get from this direct style example to this one here? So let's just go through to make sure this makes sense here. I have 2 tasks. We're going to focus on this one, this task 2, because it has more the more interesting parts in it. We want to create a task which, well, returns a type string, right? Because that's what we return in the body of this task. So we want a string here. The name should be t2. That's the name of the value here. We have a dependency on t1. We want the source code. And now the run function, which is the body of this task, should have been transformed to something like this. So the message now, so it becomes a function that takes an environment, and the message is the environment so this should be res in my example, I'm sorry, and not get, which gets the result of the first task in the environment, and also to the log passes this environment. Okay, so that's what we want. And so now how is this all strung together? Well, it's in the apply function in task. So when you wrote task colon, what you're actually doing is you're calling this apply function in the companion object of task and giving it as parameter the body of your task. And then we're going to allow the macro to inspect the inside of the body and the context function to essentially pass in the environment to the body and produce a task, which is an actual first-class object. If you're interested on a kind of high level, this macro implementation looks something like this. Again, the parameter is now an expression of the function, of the run function. In the macro, I can get the static information. Some of it I can get directly using some built-in features of Scala. So I can get, for example, the names of the declaration the macro is assigned to, and the source code as well. And to find the dependencies, what I'm going to have to do is something slightly more complex. I'll show in the next slide. But the important thing is, in the end, I'm going to produce a task which just has this name given as a literal, the sequence of dependencies. And again, here is the function. I have now just written it as a normal function literal, which is no longer a context function. So I just specify here my environment. And this way, I've transformed the direct style task into an actual instance of a first-class object here. Now, taking it another step deeper, so this is, I think, where we're going to get into territory, look this up if you're interested, is how we can manipulate, how we can really dive into the expressions and manipulate those. So here I'm using, I am going to look, so I'm going to deconstruct the expression that is passed into the function and look for any apply call to a task. So if you remember, if I say T1 open close parenthesis, this will essentially become this this tree in the Scala representation. And then I'm going to do some sneaky stuff with it. I'm going to rewrite it and return the result and also capture the dependencies. Then finally, there's one more piece to the puzzle. Again, this is, I think, you can, these are keywords to look up. If you remember in my workflow definition, I am defining tasks. So we've seen how a task can be, one task can become a first-class object. Now, to run many tasks, I somehow need my program to know all tasks that exist. I need to find them somehow, or at least the leaves, so I can work my way back. And the way you can, I have decided to do this is with type class derivation. So you see this derives pipeline. What this is essentially going to do, it's going to give me a kind of another, it's also another macro, which gets access to the outer macros and can list them all. Another way to do this is something called tasty inspection, where you can basically, once you've compiled your program, you can you just iterate through everything and try to find all tasks, or you could do something like runtime initialization as well, if you want to. So just the takeaways here of this part of the talk is really, I think that you can use macros and context functions. They pair really well to build these direct style APIs, which then boil down to first-class objects, and then you can use them in the rest of your system. It gives you like a really robust system. And I think to wrap up here now is there's often kind of two questions I get when I'm speaking with people about this. So the first one is, well, can I use this? Fortunately, not yet. As I said in the beginning, it started in its life as an internal just automation tool. So I do plan on making what you saw, the runner, the UI, making that stuff open source. But it needs cleanup work. It's part of a monorepo with the other tools, so I need to rip that out. And then there's a bunch of integration work to be done with to make it more useful. So integrating, with GitHub hooks, for example. I also want something where a build can ask a user for input, validation, can react to signals. Like the logic is there. I'm using signals already, but it's not. I haven't shown this here. And then I think there's common tasks such as cloning. You don't want to always repeat a clone task. There's some things you just want built in. Many of those can also, because it's Scala, just be developed as a library. If you do want to follow along, I don't have a timeline here, but you can follow this repository. It will land there once it's made its own thing. And the other question some people ask is, well, is this not just a build tool? What I've done, and for this I have to quote. I had this discussion with Guillaume the other day, and he said, well, if you think about it, isn't everything with a DAG a build tool? And there's this actually really nice paper which I encourage you to read. It's about a systematic way on characterizing build systems. They actually make a point, Excel is also a build tool. If you think of it, it's also a dependency graph of cells. So in a sense, yes. But I think the more serious answer is that, or the conventional answer, let's say, is that workflow engines, CI engines, build tools, they all have somewhat similar features. Modern ones are kind of converging. And it's really about the different trade-offs you make in building the system. So build tool is going to be super rigid about caching. Workflow, you don't really care so much because you just want to, some things you do care, but it's mostly you want to, for example, retry it. You want to have a nice integration into events. So triggering is very important, and interacting with the environment. Where build tool, it's you build it and you don't want to really interact with the environment. And I do have to say, however, of course, what you've seen here is the syntax and the structure I have used here exactly is pretty much inspired by the mill build tool from Howie. So that's where you see the syntax, and it will look familiar. And with that, I want to thank you for your attention.
Thank you for the talk. I really appreciate your focus on local development. My question is about applicability to environments where people use GitHub Actions already, because I noticed that many people are amazed by many people simply like to have many blocks in CI/CD environments because it looks pretty. This makes them happy. But this is at odds with efficient building of things. And well, you presented some nice graphs of dependencies, but would you have any idea how to make it both efficient, like you have, and at the same time make those people happy?
So what do you mean with the inefficient part? You're talking about like execution, or?
Yeah, basically every block on GitHub Actions is related with a startup of another process.
Well, I think if you're specifically talking about GitHub Actions where you have no control of the system, like you're not designing GitHub Actions, and one action is a container or a VM, well, you have to consider that in your design. So that's the tasks you can group in one. You need to group in one manually to say this must be part of one if you want something more efficient. I don't think there's any trick around that. It's just to say, well, maybe the tasks can be separated logically, but they can also be together. Precisely in a situation where it's linear, you don't really gain anything. I think you gain it if you have a split in your graph. But what I'm doing as well is every task is run in a separate runner, so that except locally, it's in the same runner. But what many build systems do is they allow you to, well, they have smarter scheduling. They could, for example, allow you to tag tasks that say these are part of the same environment, and then depending on the resource availability, they can, in practice, when they are run, they're going to be merged and be run in the same VM. I don't think GitHub Actions offers that, though, so mine doesn't yet, but I want to.
Hello, very cool project. I have a question about dynamic pipelines.
Yeah.
Is that something that you think that this can support?
So the direct style API, no, because it's basically, it's an applicative, not a monad, if you want to, like the term here. So every workflow will have its own, will have a rigid definition. I think it's a trade-off I made because it makes the pipeline very clear. However, a workflow can trigger another workflow. So that's how you get your dynamic pipelines in a sense.
I would like to ask, I'm GitHub Actions user, so how do tasks in your MeshCI map into GitHub workflows and jobs and things like that? Because that's related to the first question, what is the unit of the execution? Yeah. And second question is, because the GitHub Actions already have quite extensive system of existing actions and workflows, so if there is any possible cooperation between what we define in the MeshCI and the existing workflows on actions.
So, so the first question is about what the unit of execution is, right? So I think in GitHub, I think you always get one VM, right? But you can have these matrix builds that give you different VMs, right? And every step in a GitHub action is an image or a...
Gets a separate runner. There's a workflow.
Yes, each job, yeah.
Each job gets a separate runner.
Yeah. So here, basically, you have, there's no distinction between a job and a task within a job. The job is the workflow, so that's one execution, and where the tasks are run, every task can be run independently in a different environment. That's up to you. So if you run it locally, it's all going to be on your machine. You can run it in a VM, however, right? If you use public non-trusted code. So you would get everything run in a VM right now. But as I mentioned before, I think what would be really interesting is a way to tag tasks to say, like, or just deduce it of allowing tasks to specify the environments they need. If they're in the same environment, you can just merge them and run them in the same VM, right? That would be the nice answer, because they don't need to think about that.
Thanks, Jakob. Jonas here. Do you support recursive task definitions?
You mean, so with recursive, do you mean something similar to dynamic pipelines, like one task spawning another task? Is that what you're suggesting?
I guess, yeah. Or like, how do you make it so that you cannot do that with the DSL? I'm just curious about how.
So, I mean, it's not super safe. There are ways around it. If you yeah, and I'm not sure I fully understand the question, but the DSL has it helps you, right, to write the correct code, but you can do things you're not supposed to. Like you saw here, if I'm accessing an environment, I can just say, well, I'm going to be in an environment. I'm going to define a using environment in let's say, a helper function that's not in the body of the task. And now with this definition, I can access the environment, but of course, in my macro, I'm not going to find that there's a dependency. That won't work. So there's some things I can improve, like Mill does some deeper inspection of the call trees, which maybe I can reuse that thing. But there's a bunch of other things, like because I'm using Lambda serialization, you can also shoot yourself in the foot if you try to serialize something that isn't. So it's not perfect, but it helps you. In my opinion, it's still better than bash-in-YAML, because they also only find out that you have a typo at runtime.
Cool, thanks.
All right, we're out of time. So thank you, Jakob, for your talk, and let's catch him afterwards if you have more questions.
I just want to say, because I think you had, he left, the second question was about the libraries. So I don't have a plan with GitHub Action integration, but it's all Scala, so you can use Scala libraries in your build. That's it.